We will see more in the vector field, parametric, vector area, and if time permits, then we will see independence in path. Vector field, you are amazing, you are mind blowing. So, vector field, you are amazing, and vector field, you are mind blowing. So, why it is mind blowing, why it is something like that, that we will see. What is the use of vector field in real life? So, if I consider Earth or any celestial body, Earth. So, what is the gravitational pull of the Earth? So, gravitational pull of the Earth, first of all, it is a vector. Vector in the sense that if this is the spherical Earth, then it pulls as a vector. Okay, so I can say R vector. R vector in a sense that to its center it pulls in this fashion. It does not pull like this or like this. It pulls exactly towards its center of the earth. So if there is a direction, then there is a vector. So I can draw a vector calling this is the earth force. This is the force of the earth. Okay, and if this is the force of the earth, then someone would understand with the vector that this is the direction of the force. What is the magnitude of the force? As per the vector, if I describe a vector, then it has x component, y component, z component, and if I calculate x square plus y square plus z square root, that gives me the magnitude of the vector, power of the energy, and then x, y, z component gives its direction. So if I have x, y, z, then immediately I understand that what is the direction of the vector, what is the power of the vector. The force, the gravitational pull, I am not talking about the acceleration. The force with it pulls, that force I can say it is this much, this much whatever, the energy per meter. I believe that is the equation of force or some Newton per meter square. I don't remember that much. So whatever, this is the force. Now, what about this force? Is it same at all the altitude? Direction of the gravitational force pull towards Earth may be in a straight line. If I go 100 km above, but it will be towards the center of the Earth. But is the gravitational pull same 100 km above also and towards the surface of the earth? Answer is no. If someone goes 100 km above or more than that 150 km above, then probably he will be afloat. Means he would float in the kind of space. Anyway, there is no space in the universe. So these are the false beliefs. Slowly we will remove it. So universe is full. It is energy is everywhere. Space means there is no media, means there is no energy. So there is no energy means no one is there to provide any hindrance or provide any resistance to you. That's why you float. You are not under any celestial bodies pull. If you are not under any celestial body pull, and then it proves that there is no energy there, and that's how it is a space. Khaliye. In Arabic, it is khaliye. So, in khaliye or in space, there is no energy. Energy is everywhere in the universe. Oxygen is everywhere in the universe. There is no place in the universe where there is no oxygen. If human takes oxygen to survive, then each particle, each entity in space, either it is Mars or it is Pluto, these are also celestial body and they also breathe. Okay, very less, but they also need oxygen. Oxygen is considered as that air which has kind of living thing inside it. So it is required by everyone in the space. So oxygen is everywhere, energy is everywhere. But whatever, the gravitational pull at 100 km high is not the same as the what we get at the surface of the earth. This proves that the direction of the gravitational pull force is same, but its magnitude is increasing as we go near the earth. So the force is varying. If force is varying, then if I am 100 km above and if I calculate force into displacement, that how much is the energy difference between these 2 points, or how much work is done if I drop a ball from 100 km above and earth pulls it. Consider earth pulls it. Then if it pulls it, then if it travels 1 km, then how much work is done by the gravitational pull of the earth, because earth is working there. You are not working. You just drop the ball and then ball traveled 1 km. How much is the work done by the earth pull that is done on the ball for 1 km? If someone drops ball 1 km above the ground of the earth, one is 100 km, one is 1 km above the ground of the earth. If he drops the ball, then for 1 km, how much work is done? They are different. Since force is more, so if force is more, force into kilometer, force into distance is the how much work is done. So the work done by the ball, if it drops 1 km near the earth, the work done by the earth is more, and remote it is different. So here vector field, so we cannot put as a some equation or something like this. So vector field, what we understand here? So vector field, algebraic vector. Vector field means algebraic vector. Any vector has components. First component, second component, third component. If it is in Cartesian coordinate, then x component, y component, and z component. If it has three components, then I can immediately say, considering it is a position vector, then immediately I can say what is the direction of the vector. Now, if I calculate x component square, y component square, and z component square root, immediately I can say what is the power of the vector. So, if I have a situation, suppose this is x-axis and this is y-axis, this is xy plane. If I have a vector here, okay, now I have a vector field. Vector field means first, second, third component are function of x, y, and z. The first component of vector is function of x, y, z. Second component of vector is function of x, y, z. And third component of vector is function of x, y, z. Okay, if that is the case, or if I remove z, then they are function over x and y, where x and y are two independent variables. X makes x-axis, y makes y-axis, then this is xy plane. If this is xy plane and vector is a vector field where all three components of the vector are function over x and y. Consider the first component is fxy, gxy, and hxy. If that is true, then if I have a xy plane, then there is a point called x comma y. Suppose 2 comma 3. At this point, I can calculate the vector replacing x comma y 2 comma 3 in fx, gx, and hx. Then suppose vector is like this. If I move x comma y to other location and I replace x comma y value in the vector field, then vector is like this. Vector is like this. So every position xy plane for different x comma y, I have different vector that is produced by the vector field. Not only the direction. Anyone can see the direction it is changing. The strength of vector, the power of vector is also changing everywhere. That is the greatness of vector field. Vector field, when it is a function over independent components, like in 3D, function over xy xy independent variable, then the first component, second component, and third component, if there are three components or two components, they are also function over x and y. So first component also changing because of different x and y. Second component is also changing because of x and y. So altogether, vector is changing its direction based upon the x comma y. It is changing its power or magnitude based upon the x comma y. So if I have that situation, that I have a vector field where vector field keep varying its direction, vector field generates a vector when I pass independent variable. Vector field keep changing its direction when I keep changing x and y. That is one thing because it's an algebraic equation. Second thing is not only it is changing the direction, it is changing the magnitude of the vector also. Like Earth gravity. Earth gravity, Earth gravity, if we go far, then if you go far or near, the direction is same, but the magnitude of the vector is different. Okay, so I believe it is something like gm by r square, something something like that. So that is the gravitational pull that Earth shows. So r is the distance from the Earth and the body. So if r is growing, then pull is decreasing. It is something like that. Or a spring. I have a spring. I believe it should be visible. It's very small. I have a spring. If it is a spring, if I pull it, if I pull it and then leave it, okay, it should come. It's not a very well nice spring. Okay, so if I okay, so if I pull it and then leave it, okay, little bit it came, it will come to the its original position. But if I pull it and leave it, the moment I leave it, at that moment the force the spring will show to moving to original position is high. When it coming to normal position, that force, that is, suppose that I put a load here. Okay, here I attach a load, and then I pull the string. So I pull the string. Then if I leave it, the force what this load is feeling, force is more when distance is more. Force is less when it comes to its original position, then force is 0. So if I consider this force as a vector, then this is a vector field because depending upon the position, the vector field has different vector at each moment of the x. So suppose that right end of the spring is at x equal to 0. It is on x-axis. If I pull it 20 centimeter or 20 meter, consider 20 meter, then if I leave it, then if I consider that if there is a load on the right side, if load is moving back to original position, that is 0, then everywhere the force is different, it is feeling. So work done by the load is not the constant force into the displacement. That is not true. Because every moment force that this spring is feeling is different. If that is the case, then this force is, first of all, force has a direction. Force is along the x-axis. So force is I vector. It is going towards minus I, so it is minus I. And if I say it is directly proportional to the distance, then it is minus xi. Okay, so if there is some constant depending upon the vector, then it is minus k x I vector. That is the force equation, minus k x I. Okay, this is some theorem or something like that. Now if I want the work done from 20th meter to 0 meter, how much this spring has done work through this mass, it is going there, then it is force into displacement. Force vector dot with displacement vector. force vector dot dr is displacement vector d of the r. Okay. Now force is minus kxi dot d of xi, d of xi. Xi is the position vector of the ball. If I have any object in the Cartesian coordinate where it is 2D, then position vector, if it is at x position, then position vector is xi plus yj. If it is along x-axis, the position vector of the mass is xi if it is at distance x. If it is at distance x, then force what it is feeling is minus kxi minus kxi dot dxi. Okay, dxi. So d of x is dx. D of x to the power 1 is dx. So dx. Okay. So dx, and here it is minus kxi. Consider k as 1. Then it is minus x dx. If it is minus x dx, okay, if it is minus x dx, then it would turn up into x square by 2 as the integration. If it is 20 to 0, then x square by 2 I have to place lower limit as 20 and higher limit as 0. Then it will come as 20 square by 2. So it will come as 200, I believe, joule is the work done, then 200 joule. So joule by meter is the force. Joule by meter is the force. There would be other measurement also, velocity with the velocity. So mass into mv square, mass into velocity square is energy. So that is mass means kg, kg meter square per second square. If I divide it by meter, okay, then it becomes force. So kg meter by per second square. So that is the force. Okay. So it can be term of Newton and those kind of things. Now the situation what we understood now, that 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 what is the greatness? That's why I say vector field, you are great, you are awesome. Means vector field is not only talks about the direction, it talks about the magnitude also. Now next is how we can find this line integral. Dot f is a vector dot d r is a vector, where r is the path. Okay. Now we went for parametric vector. Now let's do the dissection again. So if I have a path, so consider that this path I always keep talking. Okay, if I have this path, okay, consider this is x-axis and this is y-axis. This is x-axis and this is y-axis. This is x-axis and this is y-axis. If that is the case, then this is the one line. There is a one line that intersect x-axis at suppose 1 comma 0 and intersect y-axis at 0 comma 2. If that is that, then there is a line like this. If there is a line like this, then there is also a parabolic path from these 2 points. This point is 1 0 and this point is 0 comma 2. This is x-axis, this is y-axis and this is x-axis. Now from 0 comma 2 to 1 comma 0 there is a line and there is a parabola also. This is the global minimum of the parabola and it passes through somehow through 1 comma 0. There are two. Can we calculate the line integral along this and along this? both. So what is the now against a vector field equal to xi plus yj, xi plus yj. Now, if it is like this, then vector field, if vector field is f, then f vector dot d r vector integration from lower limit to higher limit is the vector, is the line integral calculation. Now f is f1I plus f2j, where f1 is first component and f2 is second component. f1I plus f2j. If that is the case, then we have now f vector I can represent as f1I plus f2j. Since it is a vector, it has components dot d r vector. Now r is the position vector of this line. So this line at any point, consider it is xi plus yj. If this is origin, then any point is xi plus yj. Xi plus yj keep moving. This is the position vector. If that is the case, then it is f1i plus f2j, one vector dot with d xi plus yj. D of xi plus yj, if I go ahead, then differentiation of x and differentiation of y. So differentiation of x becomes 1. So this is dx, it becomes dxi plus dyj. Okay. If I differentiate xi, then it becomes dxi. If I differentiate yj, it becomes dyj. Now f vector has f1i plus f2j dot dxi plus dyj. It becomes f1 dxi, f1 dx plus f2 dy. Integration from lower limit to higher limit. Integration, if I go from here to here, then integration from 1 comma 0 to 0 comma 2. f1. So f1, the vector f1 is vector f1, f is xi plus yj. So f1 is x and f2 is y here also. So now we have x dx plus y dy. Remember this for always. f1 dx plus f2 dy is the line integral. Net. This is very detailed I talked in the last session. So f1 dx plus f2 dy. Now here it will become x dx as x square by 2. Now there y dy. Can I bring that back in dx1? So y, if I see the line vector, then what is the equation of the line? The equation of the line, if we see, then it is y equal to mx plus yz. So y equal to m is dy by dx. So dy by dx is minus 2. If I proceed 1 along x-axis, then it is backside y-axis is like that. It is not like this. If it is like this, then if I proceed 1, then y is 2. It is like this, opposite. So if I proceed 1, or if I proceed minus 1 in x direction, that is better way, minus 1 in x direction, then there is a 2 in y direction. So dy by dx is minus 2. So y equal to minus 2x plus 2 at it is passing through 0 comma 2. So minus 2x plus 2. Or if I say it is passing through 1.0, then it is minus 2 is the slope and x minus 1. Anyway, so because the equation of a line is y minus y0 equal to mx minus x0. So if that is the case, now we have y equal to minus 2x plus 2. If that is the case, then we have to replace this. Now we have integral of x dx plus y dy, f1 dx plus f2 dy. Now f2 dy. If we see f2 dy, then f2 is y and dy, y dx. Y equal to minus 2x plus 2. That I have to keep there. If that is the case, then dy equal to minus 2 dx. If y equal to minus 2x plus 2, then dy equal to minus 2 dx. Okay. If it is minus 2 dx, then minus 2 I have to multiply here in the minus 2x plus 2. So it will become minus, it will become like 4x minus 4. 4x minus 4, and this side we had x dx. So 4x and x become 5x. 5x minus 4 dx. 4x 5x square by 2 plus minus 4x. That is the integration. Now limit is 1 to 0. Now if I take only x, then 1 to 0. 0 is full 0, whereas 1 is 1 we see, then it is 4x square by 2, then it is 4 by 5x square by 2, then it is 5 by 2, and there minus 4x 4. So 5 by 2 minus 4. Just take care of the sign, whatever. So this is the integration. Now if we want parabola, if I have how it will come? So 5 by 2. 5 by 2 minus 4. It will come as 8 minus 5, 3 by 2 plus minus. Take care, 3 by 2. Now if I have a parabola, the equation of parabola is y equal to kx square plus y0, since it is making intercept on the y-axis. So y equal to kx square plus 2, because intercept it is making at 2. So kx square plus 2. Now if we substitute what is the value of k here. So when y is a kind of 0, y is 0 when x is 1. This proves that y is 0 when x is 1. Then 2 will come this side. Okay. So it becomes minus 2. So minus 2 when y is 0 when x equal to 1. So k equal to minus 2. So we deduce, so the parabolic equation is minus 2. These are well-known example. I am not taking from my mind. Minus 2 x square plus 2 is the equation of parabola. Y equal to minus 2 x square plus 2. If that is the case, now go with the same fundamental. The integral is f1 dx plus f2 dy. This is how we calculate it. If it is true, then f1 here, f1, so the vector field is xi plus yj. If vector field is x plus yj and line curve is y equal to minus 2x square plus 2, then what is line integral from 1 comma 0 to 0 comma 2? That is the question. Line integral is f vector dot d r vector. R is the line curve. R can be represented as xi plus yj. Then if I do d of xi plus yj, it becomes dxi plus dyj. If I do dot product, then f vector can be represented as first component f1i plus f2j. If I do dot product, then it becomes f1 dxi, f1 dx plus f2 dy. Here f is xi plus yj. So f1 is x. So x dx plus y dy. Now y is minus 2x square plus 2. That is the y. And dy, if y equal to that, then dy is minus 4x. If y equal to minus 2x square plus 2, then dy is minus 4x dx. So minus 4x dx multiplied by minus 2x square plus 2. So that will come as 8x to the power q. 8x to the power q minus 8x minus 2x square plus 2 multiplied by minus 4x. 8x to the power q x, okay, minus 2x square plus 2 multiplied by minus 4x. So it will come as 8x to the power 3 minus 4x minus 8x, and this side it is x dx. So x dx, and there it is minus 8x. So it will become minus 7x. Now if I integrate this, then it will become minus 8x to the power 4, x to the power 3. So it will become x to the power 4 by 4. Now if I integrate with limit 1, then minus 8 by 4, that is 2. And there it is 7x. So 7x square by 2. So 7 by 2. 7 by 2, and here it is 4. 2 minus 7 by 2, it becomes 4 minus 7, it becomes 3 by 2 again. So the line integral is not path dependent. Can you see? If I have x-axis and if I have y-axis, and there is a line that cut x-axis and y-axis, x-axis at 1 comma 0 and y-axis at 0 comma 2, there is a parabola also. It starts from this location and passes here. If I calculate line integral of vector field f and line integral of vector field f along the line, straight line and parabolic line, both are 3 by 2. Either it is plus or minus. I did not take care that much. I believe it is minus and minus, plus 2 minus 7 by 2, 4. This is minus 3 by 2. So it comes as minus 3 by 2 in the line integral also, and in the parabolic integral also, straight line integral also. So this proves that irrespective of the path, if I have beginning point and end point same, then the line integral of a vector field is same. If it is same, then if I take a circle which starts from a point and ends at same point, then the line integral will be 0. Okay, if line integral matters only beginning point and end point, if f dot dr, f vector dot dr vector, if I calculate, whatever the integral I get, that integral is same whatever dr I take. If vector field is same and limit is same, beginning point and end point is same, then it does not matter what is the r, what is the path. If that is true, then if I take a and b, lower limit and higher limit same, then it should be 0. So the closed path, if I take closed path where beginning and end path is same, and if I have a vector field, then line integral is 0. If that is the case, then this vector field is considered as path independent vector field. It's not true with all the vector field. It is true because I took x plus y. Vector field is xi plus yj. If I take something different that you can try, it will not come as 0, or it is not the same as I have this line, or I have a long line and I have another as a parabola, where the similarity is beginning end and last end are same. Otherwise, there is no similarity along the path. If a line integral is same, then this proves that the vector field is path independent. So vector field when it is path independent. Now consider that vector field, if I calculate vector field dot with the line curve and integrate it, and it sums it to a function called small f. Small f I am taking because small f signifies the algebraic equation. So vector field dot d of another vector field or path vector, if I do dot and do the integration, it comes in a algebraic equation. Algebraic equation is represented through small f, whereas vector field is represented through capital F. Okay, so f dot dr integration all along it becomes small of an algebraic equation. If that is true, then if I replace f, the capital F, whatever we have, with different gradient vector of f. F is a algebraic equation. If I have an algebraic equation, then if I calculate its gradient, means its derivative along x-axis, derivative along y-axis, then I have it is in a vector form. Whatever I get derivative along x-axis, whatever algebra I am receiving, that I can say it is a function and there is a vector called I, plus there is a function if I did provide the differentiation along y-axis j. So the gradient vector of any algebraic function is, if function is f, then df by dx I plus df by dy j. So if it is a vector, it will have I and j. Those are the unit vector x-axis, y-axis. So df by dx I plus df by dy j. If that is the case, then that is the gradient vector there. Now consider f dot dr, that converted to f1 dx plus f2 dy, if we remember it very well. So f1 dx plus f2 dy. Leave it. We will see that. Now f, the capital F. Suppose I replace with gradient vector of f, small f, capital F dot dr integration, it brings the line vector field line integral comes to a small function f, that is algebraic equation. If vector field f, capital F, in the integration, if I replace with gradient of a small f, gradient of small f, okay, then if I replace with that, then capital F dot dr, dr is d of r vector, that is nothing but d of r vector's magnitude, and here capital F, please watch all the videos, that is highly required. So capital F, that is a vector field dot dr, r is the kind of parametric vector, I mean position vector of the path. Any vector can be disintegrated into its unit vector, that is the direction, into its magnitude. So dr vector can be called r unit vector into r's magnitude. So d of r magnitude unit vector, I can take it out. If I take it out, then it is f vector dot unit vector of r. So f's component along the r vector. If I do dot with r, if this is f vector, and this is r vector, then f dot unit vector of r means f component along r vector. F component along r vector. F cross f dot r vector means f's component along r vector. F cross r unit vector. F cross r unit vector means f's perpendicular. If this is r unit vector, then r unit vector has a perpendicular vector. If this is f, then f components along the perpendicular vector of the r. F dot unit vector means f's component along the unit vector of r. If that is the case, then that f vector dot dr vector transform into f dot r unit vector dr magnitude. Okay, if that is the case, then if f Okay, f is gradient of small f that I received after doing the line integral. So f, gradient of f with dot of gradient of f. Gradient of f means it is a vector. Gradient of f, it is a vector. That vector dot with the unit vector of r. If I do, then whatever it becomes, that is a algebraic equation. That algebraic equation, if I differentiate with the dr, so that algebraic equation is nothing but f differentiation. F gradient vector of f dot the r unit vector will become the differentiation of f. If differentiation of f along r, along the r. Okay, I believe this is complex. Now consider I have a function fx. So if I say f dash x, f dash x means differentiation of fx. So if I have f dash x dx integration, then isn't it equal to fx? F dash x df by dx integration is nothing but it will lead to f dash x dx is f. So f dash x dx is nothing but f, and then limit is lower limit to higher limit. So whatever the f algebraic equation I have, if I set higher limit and lower limit, if I differentiate it, then I get the f dash x dx. Now here, similarly, I had f vector, capital F vector dot dr, that transformed into small f, capital F vector dot dr vector. If I do the line integral and then do all the computation, it leads to a small f function. So capital F, if I replace, suppose if I replace with gradient vector of f, gradient vector of f. If that is true, then gradient vector of f dot I, gradient vector of f, gradient vector of f, small f, that I got through line integral. Gradient vector of small f dot unit vector of r, that leads to the f dot r, means the differentiation of f dot r. Isn't it becomes f? F dot if dash r dr becomes f. If it becomes f, then it proves that now f we have to f. So this is what we were doing. Capital F dot dr, that integration becomes f. But if I change capital F with gradient vector of f, it becomes same thing. This proves that if I have, now I have lower limit and higher limit. So it is nothing but that if I have, okay, so if I have capital F, if I say capital F, not f dot dr vector, if capital F is gradient of small f, if capital F vector dot dr, the integration what we are calculating, if that becomes f, okay, if that becomes f, then if I replace capital F with gradient of f, then result is same. Anyway, it is same. If I have capital F dot dr, then capital F is nothing but differentiation of f only, df by dr. If I have df by, one is capital F, that is vector field, one is small f, that is the line integral. If I replace capital F with small f by dr, small f by dr, and then dr, then it becomes f1. This is what we are doing. So the idea is, if I have a vector field capital F dot dr as a whole, and it leads to a algebraic equation small f, And if this f is equal to gradient vector of small f, or in other way, if I am able to calculate gradient vector, if capital F is equal to gradient vector of some algebraic equation, then this capital F dot dr can be replaced with f. If that can be replaced with f, then now full integration is small f. Now we have lower limit and higher limit. If that is true, can you see this, that the capital F dot dr, capital F dot dr, whereas capital F equal to gradient of small f that I received through line integral. So small f is nothing but only dependent upon f. Please mind it. If I have capital F, that is vector field, capital F is a vector field, dot dr is the line path, dot dr integration. If that results into small f, so small f is algebraic function or the vector field's line integral. If I am able to replace capital F with gradient of f, then result is same. This proves that the f what we are calculating, that is only dependent upon capital F, not on the dr. If that is true, then if I prove that my capital F has a small f whose gradient vector is capital F, or I have any function f whose gradient vector is capital F, then I don't worry about the dr part at all. If that is the case, the line integral of vector field along any path is nothing but the f, just f, then lower limit and higher limit. So that is line integral of any gradient vector along a path is dependent only upon the beginning path and end path if this vector field has a function, there is a function that is available whose gradient vector is capital F. Not necessary. For all the capital F, calculating a function whose gradient vector is f is not possible. But for all the f for which there is an algebraic function exists whose gradient vector is equal to capital F vector field, if that is the case, then vector field is called path independent, because if for capital F there is a function exists for which gradient of f is available, then I can replace capital F with gradient of f. If I replace with gradient of f, then d of r vector turns into r vector unit vector and magnitude of r. Unit vector I can take it out, then it becomes gradient of small f dot unit vector of r d of r magnitude. Then these two dot, it leads to df by dr, d small f by dr, that would leads to f. So if capital F gradient vector field has for that gradient vector field there exists a algebraic function small f for which gradient vector is same as capital vector f, then it is path independent in the sense that now it only depends upon the lower limit and higher limit. Okay, other way also we can prove it. Now consider that I have capital F is the gradient field dot dr. If r is described as xi plus yj, then it becomes, if f has component as f1i plus f2j, then it is f1i plus f2j dot dxi plus dyj. It results in f1 dx plus f2 dy. If that is the case, then integration, if I calculate, then f1 dx I have to do integration, and if integration to calculate what, because f1 dx plus fy dy would result in an algebraic equation. If it results in an algebraic equation, then f1 dx or f1 f, the vector field's x component, first component dx, that is the integration. If I calculate, then first component fx is nothing but whatever algebraic equation I am calculating, its partial derivative along x-axis. That's why it is dx. And capital F vector y, the second component dy, what it would result in algebraic equation. That algebraic equation, if I do partial derivative along y-axis, that is nothing but fy. So capital Fx and capital Fy, capital Fx dx plus capital Fy dy, where capital F is vector field and small f is the vector field's line integral. So small f, if I do partial derivative along x-axis, and if it is fx, then fx dx. If I do partial derivative along y-axis, and if it is fy, then fy dy. All along, it becomes the small f. If this is proved here also. Now, if that is the case, then capital Fx dx plus capital Fy dy is nothing but small f. If it is small f, then small f is f capital Fx dx plus capital Fy dy. Then if it is small f, then df by dx is capital Fx, d small f by dx, partial derivative along x-axis, is capital Fx, first component of capital F, and df by dy is Fy, that is second component of vector field capital F. If that is the case, then we can replace capital Fx dx plus capital Fy dy with simple small f that would have resulted in the line vector. Now, if that is the case, then whatever we were doing the line integral calculation, this is only dependent upon the lower limit and higher limit. If that is the case, then the capital F vector field is considered as path independent. If it is path independent, then we can, the way we calculated, you remember the parabola we calculated with so much pain. Parabola we calculated with so much pain. Line also we calculated with so much pain. Line equation was y equal to minus 2x plus 2. This is what I remember. If that is true, then xi plus yj is the vector field. So x dx plus y dy. Then x dx and y dy we brought it into x form only. Then we added, then we did integration and then lower limit to higher limit. But then we get the small f. But small f can be received through capital F only. dr is not required. The line is not required because it is dependent upon the beginning point and end point only. That is, it is dependent upon the lower limit and higher limit of the integration. And if capital F can be represented as gradient of f, then gradient of f means f can be received through capital F only. R is not required. So if capital F is x plus y, if capital F is x, if capital F is xi plus yj, xi plus yj, then it is equal to gradient of f. So gradient of f, then what is f? X component. Okay, so f, gradient of f is f1i plus f2j. If that is true, then gradient of f means if I differentiate f with along x-axis, that becomes f1. If that is true, then fx, the differentiation of the small f along x-axis, partial derivation, is f1. So x now if I do x dx, then it becomes the function f. If that is true, then x dx is x square by 2. So function f is x square by 2. If I derive it along x-axis, then it becomes 2x. But where is the y component? So I can say that the fx dx, integration of fx dx, capital Fx dx, that is xi, that becomes x dx, then it becomes the the x square by 2. So x square by 2 plus any function of y1. If I say cy, any function over y, x square by 2 plus any function of y1, that is the small f. If I do small f df by dx, then it becomes 2, then it becomes x square by 2 becomes x I plus any function of cy goes up. So what function I am receiving? I am trying to get the algebraic function f only through capital F, not through the line or parabola, because this is what we have proved, that if there is a function exists whose gradient vector is capital F, then it is path independent. If it is path independent, then f capital F dot dr vector, r vector I don't mind, only vector field matters. If that is the case, then capital F, from capital F I have to find small f. Now capital F has x component and y component. If I integrate capital F x component, that is xi, then I get the x square by 2 plus any function of y1. If that is the small f, then df by dx equal to x plus 0. I get the xi. Okay. Now, if that is the case, then I have got a small function algebraic equation as a small f equal to x square by 2 plus any function of fy, any function of y. If that is true, then if I calculate the partial derivative along x-axis, that exactly becomes the first component of vector field, that is x, xi plus nothing. Now, if that is the case, now if I got the f, that is the vector field line integral, then what is df by dy, d small f by dy? If I calculate d small f by dy, then x square 2 will go away, and then another, that is dcy by dy. dc by dy equal to y. We have seen the vector field is xi plus yj. So if it is xi plus yj, from vector field f, I am trying to get the algebraic equation small f, where gradient of a small f is capital. So first I integrated the first component of f to get the f. So f I got x square by 2 plus any function over y. If that is true, then df by dy, d small f by dy, that is partial derivative along y-axis, equal to dcy, any function over y that considered is cy, dcy by dy. That is yj, that is the vector field y component. So if any function derivative is y, then it is y square by 2. So now function is changed to x square by 2, the small f. F is x square by 2 plus any function over c. Any function over c becomes y square by 2. So now the integral is the line integral of vector field x plus yj along line aligned is x square by 2 plus y square by 2, limit from 1 to 0, okay, or 1 0 to 0 2. Let's substitute. So 0 2, up is 0 2, then it becomes 2 to the power 2 by 2, 2, 4 by 2, 2, minus 1 0, 4 by 2, that is 2, minus 1 0, that is 1 by 2. So 2 minus 1 by 2 becomes 3 by 2. Same. So now what is the line integral of a vector field xi plus yj along the parabola? Now I know that since there is a function exists x square plus x square by 2 plus y square by 2, if that function, if I calculate gradient, that is xi plus yj, that is nothing but exactly vector field, that is xi plus yj. So if there is any function exists whose gradient is a vector field, then this vector field is path independent. If that is the case, then if I want to calculate the line integral of a vector field from one point to another point, it doesn't matter which path it takes. Now, what is the line integral of a vector field xi plus yj along a line that intersects x-axis at 1, 0, y-axis at 0, 2, or a parabola that has equation same thing as minus 2x square plus 2, or a circle like this, or a cone like this, doesn't matter. Everything is 3 by 2 or minus 3 by 2. Okay, so this is concept of independence, path independent as far as vector field is concerned. If that is true, then if I have a earth gravitational force pull, that is the vector field, for that vector field, if I prove, so this is the questionnaire. So if I have the gravitational pull of the earth, I believe that is some constant, r vector divided by r to the power 3 minus minus k, some constant, minus k r vector divided by r to the power 3, where r vector is the position vector of the item. So if this is earth surface, and item is here, then from earth origin this is the position vector, that is r vector. If this is r vector, the gravitational pull is minus because it is towards the origin. So minus k, some constant r vector divided by r to the power 3. If this is the case, then someone has to prove that if this is the vector field minus k, I believe it is gmm, something like that. If it is minus k r vector divided by r to the power 3, if this is the vector field, question of the vector field, then it is path independent. If this is path independent, then I have to calculate a small f whose gradient is this, vector field. If I know that function f, then if I want any line, any gradient, any vector field line integral between 2 points, then irrespective of a straight line or this line or that line, the gradient vector field line integral would be same because it will be f, whatever the gradient line vector equation I have calculated, that is lower limit and higher limit I have to just calculate. That's it. Begin point, end point. If this proves that if I drop a ball or a person is jumping from a building, don't jump from a building. I would change it. If I drop an item from a building, then how much energy, how much work done by gravitational pull on that item has been done. That means how much energy Earth transferred on that item, or how much energy that object carries at that moment. So that small f is also called potential function because it has potential energy. So this is also called, so vector field line integral is also called potential function. If this is if this is if this is if this is potential function, then if I have a ball in my hand, if I drop the ball, then it loses energy. At this moment it has the energy, and when it hits the ground it has the zero energy. How much energy it lost, or what is the work done by the gravitational pull on this ball, whatever is considered. Now, if I drop this ball on the floor where it is going by stair, dub, 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 and then finally from a 100-story tall building, it is going slowly, dub, 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 and hitting the ground, then the work done by the earth on this ball through the force gravitational pull, and if I drop, both are same because the gravitational pull force has a potential function whose gradient vector is the gravitational pull. If I proved it, then this is path independent. So capital F dot dr, that is the line integral function that transforms into small f, that is algebraic. If it transforms to small f, then it is just mere calculating the lower limit and higher limit. So higher limit is the 100th floor of the building and lower limit is the ground. So if I have algebraic equation of the potential function, then just set this 100 and 0, then you get the how much is the energy difference between these two. That much is the work done by the earth, or that much energy it lost, or if I go from here and there, that much potential energy it got. Okay, so this is the questionnaire, that if I have earth pull, equation is minus k r vector divided by r to the power 3, then prove it that it is path independent. How to prove it? You have to think about one imaginary function whose gradient vector is this this vector, that is minus k r vector divided by r to the power 3. If that is true, then integrating this vector field f along r would result in the, if I integrate this, then this should is result in the potential field. So straightforward, right? What is there in this? So easy. Means that you have to calculate, that is there. Now you can check with the Cartesian coordinates. These are very known example you will find on internet also. This is not my example. You can check back with the kind of xy coordinate. Okay, so this is kind of a path independence in in calculate in vector field line integral. So if I have a vector field, and if I prove that there exists a potential function small f whose gradient vector is this vector field, then no need to calculate dot dr and then bring it dx f1x plus fy dy, and then x and y you have to do, and then integration. For each line, each path you have to keep doing and calculate the line vector. Just for the capital F gradient vector, calculate the potential function and just sweep it everything, whatever you had f dot dr, and replace with function f, that is a potential function, and calculate the lower limit and higher limit. That is the energy difference between these two. That's it. Now, that vector field from this point to this point, either you take a straight line or zigzag or maze or a parabola or a circle, whatever, it doesn't matter. Line integral is same. Only thing you have to prove that for a particular vector field, there is a vector, there is a algebraic function exists or potential function exists. For gradient of that potential function is the vector. Okay, so for every vector field, for vector field x plus xi plus yj, we calculated the function f, that is x square by 2 plus y square by 2. For every vector field, this integration is not possible. So every vector field is not line independent. Okay, so we will see more on it, and then finally we will enter into 3D. We are talking about parabola, line. We'll talk about surface, paraboloid, and something like that. So that is even more important, and there the parametric vector will come into the prominence. That is the idea. So that we'll see.